For n-dimensional array where n is greater or equal to 4, this is referring to 4-dimensional array, 5-dimensional array, and above. There's only one way to order the elements, and that is using the row major order. We have here the indices of the n dimensions, where the first dimension, the index is S1. For the second dimension, it is S2. The index for the third dimension is S3, and so on, up to Sn, the index of the nth dimension. Just like in the 1D, 2D, and 3D, we denote the base value and the upper value with B and U. So for the first index or the first dimension index, the base value is B1 and the upper is U1. For the second dimension index, it is B2 and U2. For the third dimension index, S3, it is B3 to U3. And in general, for any value of n, for the nth index, Sn, the base value is Bn and the upper value is Un. So let's take a look at the addressing function. So if we're going to locate an array element, say the array name is A, and there are n indices, S1, S2, S3 up to Sn, the formula is the same. Just like in 1D, 2D, and 3D, we start with L sub O, which is equal to 1. S1 minus the base of S1 multiplied by the number of elements in the first dimension, considering the first dimension. And this number of elements is a product of the size of the second dimension. Okay, so this is size 2. The size of the third dimension, say this is size 3, up to the size of the nth dimension or size n. And then we add the next index here is S2 minus the base of S2, which is B2, and this is the number of elements in the intersection of S1, the first dimension, and the second dimension. So again, this is the total number of elements in the intersection of dimension 1 and dimension 2. And that is simply equal to the product of the size of, this is the size of the third dimension times the size of the fourth dimension up to the size of the nth dimension. Next is S3. So we say S3 minus the base of S3, which is B3, times this is the total number of elements in the intersection of dimension 1 and dimension 2 and dimension 3. And this total elements is simply a product of the size of the fourth dimension times the size of the fifth dimension up to the size of the nth dimension until we reach here. The second to the last index, which is S sub n minus 1 minus the base of that, which is Bn minus 1. And we multiply it with the total number of elements in the intersection of D1, dimension 1, dimension 2, dimension 3, intersection up to the dimension n minus 1. So the intersection of that, you count how many elements are there. That is that value, which is the size of the nth dimension. And lastly, we say S sub n minus Bn, the base of Sn, times that is 1. Just like in 1D, 2D, and 3D, this is times 1, meaning there is only one element in the intersection of dimension 1, dimension 2, up to dimension n. So intersecting all the n dimensions, that is only one element, just like in the 2D and 3D. So say for example, we have 6-dimensional array. So the index would be up to 6. We have S1, S2 up to S6. So when we locate for the element whose indices are this S1, S2 up to S6, we would say L sub O plus S1 minus B1 times this is the size of the second dimension. This is the size of the third dimension up to the size of the sixth dimension. And that is the result of that, or the value of that, is simply the total number of elements in one value of the first dimension. And then plus S2 minus B2, and then this is the total number of elements in the intersection of dimension 1 and dimension 2. And that is equal to the size of the third dimension times the size of the fourth dimension times the size of the fifth dimension times the size of the sixth dimension. And then plus S3 minus B3, the base of S3, times this is the total number of elements in the intersection of D1, D2, and D3. And that is simply equal to this is the size of the fourth dimension times the size of the fifth dimension times the size of the sixth dimension. And then plus S4 minus the base of this index times this is equal to the total number of elements in the intersection of dimension 1, dimension 2, dimension 3, dimension 4. And that is equal to, that is the size of the fifth dimension times the size of the sixth dimension. And then next is S5 minus the base of this index S5 times this is the total number of elements in the intersection of D1, dimension 1, dimension 2, dimension 3, dimension 4, and dimension 5. And that is equal to the size of the sixth dimension. And finally, the last index is S6 minus the base of S6 times 1. And that one is simply the total number of elements in the intersection of the first dimension, second dimension, third dimension, the fourth dimension, the fifth dimension, and the sixth dimension, and that is simply equal to 1. So intersecting all the dimensions, the 6 dimensions, that would be only one element. One element is found in the intersection of all the 6 dimensions. The general addressing function for n-dimensional array where n is greater or equal to 4 can be rewritten this way: L sub O plus the summation, take note that that is summation of Si minus Bi times Pi, where I is from 1 to n. Your I is from 1 to n. And this part here, this and this, up to that, is represented by this Pi, where this Pi here is equal to the product of the expression Uj minus Bj plus 1, where j is from I plus 1 to n. So when I is equal to 1, this would be L sub O plus, okay, the first term here would be, when I is 1, would be S1 minus B1 times our P1. Our P1 here is equal to, that is equal to the product of U, since I is 1, P1, J would be from 2 up to N, right? Because it is I plus 1. So if I is 1, then your J here would start with 1 plus 1, that's 2, 2 to N. Okay, so this would be U2 minus B2 plus 1 times, this is equal to 6. In this example, this would be times U3 minus B3 plus 1 up to U6 minus B6 plus 1. Okay, that is your P1. Okay, and then plus, the next I is 2, S2 minus B2 times P2. The P2 here, according to this, is now equal to, your I now is equal to 2. And so your J would start from 2 plus 1. That would be 3 to 6. So this is U3 minus B3 plus 1 times U4 minus B4 plus 1 times up to U6 minus B6 plus 1. So the end term is always index or subscript 6. So if I is 1, J would start with 2. If I is 2, J would start with 3. Okay, as you can see here in our formula. Say we are now second to the last. This would be S5 minus B5 times P5. What is P5? P5 is simply, based on that, U6 minus B6 plus 1, which is this one. Or in our example here, this one. And finally, the last, when n is equal to 6, okay, in this example, our n is 6. So we have S6 minus B6 times P6. P6 is what? This is I is 6, so this would be 7. So since that does not exist, then this is simply 1. Okay, so let's have an example. Say we have here a 4-dimensional array. So our n is equal to 4. And the total elements now would be the product of all the sizes. So 2 times 3, this is 2, times 3, times 2, times 2. So 2 times 3 times 2 times 2, this is 6 times 4. 6 times 4 is, total is 24 elements. And in the row major order, since n is 4, and as we have discussed before, for n greater or equal to 4, there is only one way to order the elements, and that is by using the row major order. The indices now are S1, S2, S3 up to S4, and by default, the indices start with value 0. And so, since that is 2, for the first dimension, this would be 0 to 1. Since that is 3, this would be 0 to 2. And that is 2, so this is 0 to 1. And the last one, the fourth dimension, is from 0 to 1, since that is 2. So this is your B1, B2, B3, B4. This is U1, U2, U3, and U4. To get the sizes of the 4 dimensions, for the first dimension, that would be U1 minus B1 plus 1, which gives you 2. And for the second dimension, that would be U2 minus B2 plus 1, that gives you 3. And for the third dimension, the size is U3 minus B3 plus 1, that's 2. And for the last and the fourth dimension, it is given as U4 minus B4 plus 1, which is equal to 2. So that's 2 by 3 by 2 by 2, as given above. If we're going to list now the elements in the row major order as they are stored in the RAM, we start with these indices and end with all of these indices. Okay, so it's from 0, 0, 0, 0, and then how many S4 are there? How many values? It's 0 and 1. So we have 0, 1. After that, we move to the next S3 value, which is from 0, this becomes 1. Okay, and then 0, 1 for all values. Then after that, since that is the last value for S3, 1, we move to the next value of S2, which is S2 now would become 1, and S3 and S4 are back to 0. So for this value of S2, 1, we have 0, 1 for this S3 value, and then 0, 1 for this S3 value for all values of S2 equal to 1. After that, we increment S2. S2 now becomes 2, the last value, and reset again back to 0, the S3 and S4. So for all values of S4, 0, 1, and then increment S3 for all values of S4, and then after that, increment S2, and after that, since this is the last value of S2, we increment S1. So S1 here becomes 1, and S2, S3, S4 are reset back to 0. And we start again with the 0, 1 for S4 for this value of S3, and then another new value for S3, 0 and 1 for S4. And then we increment S2, reset S3 and S4 again for values of S4, 0, 1, S3 is 0. For values of S4, 0, 1, S3 is 1. And after that, we increment S2. S2 now is equal to 2, the last value. So this will be 1, 2, and reset the S3 and S4 back to 0. So for all values of S4, 0, 1 for this value of S3, increment S3, it's now 1 for all values of S4. Okay, so this is the first element with these indices, all zeros, and the last element, the 24th element, has indices which are all of these values 1, 2, 1, 1. Now that we have listed all the elements in its row major order, so this is the first element, this is the 12th element, the 13th element, and this is the 24th element. Okay? So let's try to find this element, which is the one located at the 12th position with the indices 0, 2, 1, 1. And using the addressing function, we say locate, the indices are 0, 2, 1, 1. So the values of S1, S2, S3, S4 are 0, 2, 1, 1 respectively. So L sub O here is equal to 1. So that's 1 plus S1 is 0. That is your S1 minus B1, 0, times the sizes of the second, third, and fourth dimension, which are this, 3, 2, and 2. So we say 3 times 2 times 2, plus this is your S2 minus B2. So again, this one here is your S1 and B1. And this is the product of the size of the third dimension and the fourth dimension. So that's 2 times 2. So we have here 2 times 2. Plus this is S3. S3 is 1 minus B3, which is 0, times this is the size of the fourth dimension, which is 2. here. Okay, so that's 2 plus, this is your S4, 1 minus B4, 0 times 1, the last. Okay, so this would now be 1 plus this part here is 0, cancel out, that's 0. And then this is 2 times 4, that gives you 8. This is 1 times 2, that's 2. And 1 times 1 is 1. So add all, 8, 9, 10, 11, 12. So our addressing function returns to us this value 12, meaning that the element A0211 is located on this position in the array structure as stored in the RAM. Okay, so we get a consistent value 12.